Bismillahirrahmanirrahim. Assalamu alaikum students, this is Hamza Noor and today we are going to solve some questions from the past papers of A-level Maths P1 Cambridge, and specifically I'm going to solve the questions based on the topic domain and range of composite functions. So first of all, we have handout question number 27, which is February-March 2017, paper 1 variant 2, question number 8. So the question says that the functions f and g are defined for x is greater than or equals to 0 by fx function is 2x squared plus 3 and gx is a linear function which is 3x plus 2. The requirement of part 1 is to show that g of fx is equals to 6x squared plus 11, and we need to obtain an unsimplified expression for f of gx as well. This question is worth This part is worth 2 marks. So first of all, what we have is gx function, which is 3x plus 2. So the input for gx function is x. So now we need g of fx, meaning the input of the gx function will become fx itself. So 3 times fx and then plus 2. Okay, the input of the gx function is now fx itself. So in place of x, I'm going to substitute fx function. So therefore, I'm going to say that g of fx is equals to 3 times 2x square plus 3 and then plus 2. All right. So far, we have achieved this thing. So now we can say that g of fx is equals to 6x square plus 9 and then plus 2. So therefore, g of fx is equals to 6x square plus 11. All right. And then we need to obtain an unsimplified expression for f of gx as well. Okay, so fx function is basically 2x square plus 3. So f of gx means that input of the fx function is now gx itself. So this becomes 2 times gx whole squared plus 3. Okay. So this essentially means that f of gx is equals to 2 times 3x plus 2 whole squared plus 3. Okay, we need just an unsimplified expression for f of gx. So you have to find g of fx and f of gx over here, and this complete working is worth 2 marks. All right. So now we have part 2. Part 2 says that find an expression for inverse of fgx function, and we need to also find the domain of the inverse of fg. Okay, this means that this is an inverse of the fgx function. All right. Fg inverse x is something else, and the inverse of fgx function is something else. In this case, we have inverse of fgx function. Okay, inverse of fgx function. So what we need to do, first of all, we need to find the function f of gx, which we have already found in part 1. Okay, so first of all, we are going to equate f of gx with y. So y will be equals to 2 times 3x plus 2 whole squared and then plus 3. All right. So now we need to make x the subject. So we can say that 3x plus 2 whole squared is equals to y minus 3 completely divided by 2. So taking square root on both sides, 3x plus 2 is equals to plus minus under root of y minus 3 completely over 2. All right. And then we can say 3x is equals to minus 2 plus minus under root of y minus 3 completely over 2. All right. And then we can say that x is equals to 1 over 3 is completely multiplied by minus 2 plus minus under root of y minus 3 over 2. Okay. And we can write this thing as well. X is equals to minus 2 over 3 plus minus 1 over 3 into under root of y minus 3 completely over 2. Okay. So now in place of x, what I'm going to do, I'm going to write inverse of f g x. In place of y, I'm going to write x. But I need to decide if we have to keep the positive sign over here or the negative sign. And for that purpose, we need the range of the inverse of f g x function. And for that purpose, we essentially need the domain of f g x function. Okay, so first of all, we would need to find the domain of the composite function f g x. We need to find the domain of f of gx first. All right. So as we know the matter of fact that the domain of the composite function is either the same as the domain of the inner function or else lies inside it. So as we can see that the domain of the inner function is that x is greater than or equal to 0. Both the functions actually over here are having the domain x is greater than or equal to 0. Either it is fx or gx. So this thing will become the domain of the composite function. So therefore we can say that the domain of f of gx is that x is greater than or equal to 0. Okay. In almost all of the cases, the domain of the composite function is the same as the domain of the inner function. So you just need to simply state this thing first, that the domain of f g x is x is greater than or equal to 0. Okay, because this is the domain of the inner function. All right, and now this will become the range of the inverse of f g x function. So therefore I'm going to say that the range of the inverse of f g x, it is that inverse of f g x is greater than or equal to 0. All right. So now in place of x, I'm going to write the inverse of f g x. Okay. And in place of y, I'm going to write x. Okay. And the outputs for the inverse of f g x, I need greater than or equal to 0. So obviously in minus 2 over 3, I need to add something. So this essentially means that the positive sign will come over here. Okay, so now I'm going to say that therefore the inverse of f g x is that minus 2 over 3 plus 1 over 3 multiplied by under root of x minus 3 completely over 2. This is supposed to be your inverse of f g x. Either you can write your answer in this way, or you can simply write, first you can write 1 over 3 multiplied by under root of x minus 3 over 2 and then minus 2 over 3. Both ways would be acceptable. All right. So here it is the inverse of this fgx function. And we also need to find the domain of the inverse of fgx. Okay. So as we know the fact that the domain of the inverse function is the range of the original function. So first of all, we would need to find the range, we would need to find the range of f of gx. Okay, so first of all, we need to find the range of f of gx. So as we know the matter of fact that the range of the composite function is either the same as the range of the outer function or else lies inside it. So here what we are going to do, we are going to find the range of the outer function, which is fx. Gx is the inner function. In this case, gx is the inner function. I mean the first function, the inner function, and fx is the outer function, meaning the second function. Okay, so we need to find the range of fx over here. And as you know the fact that the composite function only exists meaning if f of gx exists, so the range of g must be contained within the domain of f. Okay, so first of all, we need to find the range of G, because the range of G will be contained within the domain of F in order to make sure that the composition FGX exists over here. And obviously this exists over here. Okay. And what we need to find first the range of GX function. And that range of GX will be used as the domain of the outer function, and then we are going to obtain the range of the outer function, which will eventually be the range of the composite function f of gx. Okay, so as we know the fact that gx is a linear function, 3x plus 2. Okay, and both functions have the domain x is greater than or equal to 0. So gx has the domain x is greater than or equal to 0. Okay, so the input of gx function is equal to 0, so 3 times 0 and then plus 2. So when input of the function gx is 0, so output is 2. So this means that here we have the gx graph for the restricted domain that x is greater than or equal to 0, and the range of gx function would be gx is greater than or equals to 2. Okay, this is the range of gx. Now this will become the domain of fx, domain of the outer function. Okay, so because in order to make sure that the composite function fgx exists, the range of g must be contained within the domain of f. Okay, so what we know the fact is that the fx function over here is 2x squared plus 3. Fx function is 2x squared plus 3. And now the range of this gx function will become the domain of fx function. So now we are going to sketch the fx function over here for this domain that x is greater than or equals to 2. So 2x squared plus 3, meaning you have a least standing point quadratic graph. Okay, so 2x squared plus 3. So, if there was not any restriction on the domain of fx, so fx graph would be something like this, least standing point quadratic graph. Okay, where the least standing point would be when x is 0, y is 3. However, now fx has a restriction that x is greater than or equals to 2, because the range of the inner function is gx is greater than or equals to 2. This will become the domain of fx function. So now in place of, you know, inside the fx function, we are going to substitute 2. So f2 is 2 times 2 is square plus 3. So 2 times 8 plus 3, this is 11. So f2 is basically 11. So now what we can see over here is that fx function would be something like this, that when input of the function is 2, so output is 11. Make sense? All right. So now we can say that the range of the outer function, meaning the range of the second function, the range of fx is that fx is greater than or equals to 11. This will become the range of the composite function fgx. Okay, therefore we are going to say that the range of fgx function is that f of gx is greater than or equals to 11. Okay, so this is now the range of f of gx. This will become the domain of the inverse of fgx function. So therefore, we are going to say that domain of inverse of fgx function, this is supposed to be x is greater than or equals to 11. This is supposed to be our answer. I mean the domain of the inverse of f g x function. Okay, so here we have solved part 2. And here we also have an alternative approach in order to find the range of f of gx function. So I'll just do this alternative approach over here. Since we know the fact that the f of gx function, the f of gx function is basically the unsimplified expression 2 times 3x plus 2 whole squared, 2 times 3x plus 2 whole squared, and then plus 3. And we already know that the domain of f of gx is that x is greater than or equals to 0, which is the domain of the inner function. All right. So what we are going to do, we are going to make a sketch for the graph of f of gx function over here for this restricted domain that x is greater than or equals to 0, so that we would be able to find the range of the composite function f of gx. So here we have the completing square form, not exactly the completing square form which you have studied, which is like a times x minus h whole squared plus k. But if I need to convert this into this form, a times x minus h whole squared plus k, so I'll just show you some extra steps over here. So 2 is already outside, and when 3 comes outside, so it brings the power 2 as well along with itself, and then this first term becomes x, and then plus 2 over 3 is whole squared, and then plus 3. Okay, so 2 times 3 square, this will give you 18. So 18 times x plus 2 over 3 whole squared plus 3. These extra steps can be helpful for you at some points, but this working is uh, extra, far more extra. Uh, you don't need to do these steps over here, particularly in this question. I'm just giving you some detailed explanation over here. Okay, if you want to arrange the completing square form in the form which you are already studying since the start, all right, which is a times x minus h whole squared plus k. Even if you do not use this, you can still use this unsimplified expression which you obtained in part 1, which was 2 times 3x plus 2 whole squared plus 3. Okay, but for some extra explanation, I have shown these steps. Okay, you can make this thing easier for yourself in this way as well. Like, for example, if you have ax plus b whole thing raised to the power of n, and you need to factorize it in such a form that the coefficient of x inside the bracket becomes 1. So when a is taken outside, so it brings the power n along with itself. And inside you have x and then plus b over a, whole thing is raised to the power of n. Even if you do not remember this step, what you can do over here is that, you can use the rules of indices. You can perform one additional step over here as well. Okay, meaning if you take a as common, you are left with x plus b over a inside, and this complete whole thing is raised to the power of n, meaning the power n is on a as well, and it is on the expression x plus b over a as well. All right. So in the very next step, you can say a raised to the power of n multiplied by x plus b over a whole thing raised to the power of n. All right. Since according to laws of indices, what you know the fact is that a times b whole thing raised to the power of n is exactly the same thing as saying a raised to the power of n multiplied by b raised to the power of n. All right. Anyways, this complete explanation was way too extra over here. I was just trying to give you some detailed explanation over here. So our concern is with this unsimplified expression. Okay. So when the bracket is equated with 0, so 3x plus 2 is equal to 0. So x is equal to minus 2 over 3. and this 3 is equated with y. So y is equals to 3. Therefore, we can say that minus 2 over 3 comma 3 is the turning point of the quadratic graph. Okay, minus 2 over 3 comma 3 is the turning point of the fgx quadratic graph, f of gx function over here. And even if you use this completing square form, you will get the same thing. As you already know that when you have the completing square form, a times x minus h whole squared plus k. So whatever is inside the bracket, meaning x minus h over here, so x minus h is equated with 0. So x is equals to h and y is equals to k. So therefore you say that h comma k is basically the turning point of the quadratic graph. Okay, so in the same way, x plus 2 over 3 is equated with 0. So x is equals to minus 2 over 3 and y is equated with 3. So minus 2 over 3 comma 3 is the turning point of the quadratic graph. All right. So now I'm going to erase this extra explanation over here. All right. So now we can actually find the range of the composite function by this alternative approach, which I'm trying to explain. Okay, so far we have achieved that minus 2 over 3 comma 3 is the turning point of the quadratic graph over here. So if I make a sketch for this f of gx function, I'm going to make a rough sketch over here. So minus 2 over 3 comma 3 is the turning point of the quadratic graph. Let's say x is equals to minus 2 over 3 over here and y is equals to 3 over here. So if there was not any restriction on the f of gx graph, the quadratic graph would look something like this. However, there is a restriction that the domain of f of gx is that x is greater than or equal to 0. So this essentially means that we are interested in finding the y-intercept over here. Okay, so now I'm going to substitute x is equal to 0 into this function. All right, so 2 times 2 is square and then plus 3. So 2 times 4 and plus 3, this will be 11. So therefore, I'm going to keep the graph only for the domain x is greater than or equal to 0. X is greater than or equal to 0. All right, and I'm going to erase the remaining part of the graph. And therefore, by the sketch of the quadratic graph, we can see that the range of f of gx is that f of gx is greater than or equals to 11. This is the range of the composite function, range of f of gx, and this will become the domain of inverse of fg. As simple as that. Okay, so this was basically an alternative approach. All right, this range of fgx will become the domain of inverse of fgx, which we have seen earlier. All right, so now let's move on to part 3 and complete this question. I'll bring the picture of the question on the next page over here. I'll make a separator over here and bring the picture. So in part 3, it says that solve the equation gf2x is equals to fgx. We need to solve this equation. Okay, so first of all, what we know the fact is that g of fx is 6x square plus 11. So g of f2x means the input of this composite function is now 2x. So 6 times 2x whole squared plus 11, which means 24x square plus 11. Agreed? 6 times 4x square plus 11. So g of f2x, this is equals to 24x square plus 11. And we need to keep this equals to the f of gx function. So f of gx we already obtained, which was 2 times 3x plus 2 whole square plus 3. Okay, so f of gx was equal to 2 times 3x plus 2 whole square plus 3. ऐसा ही है ना भाई? Uh, yes. All right. So we need to keep these two functions equal, and we need to solve the equation over here. So 24x square plus 11 is equal to what? 2 times, I'm going to expand this, 3x plus 2 whole square. So a square plus 2ab plus b square and then plus 3 in the end. Okay, so in place of a, 3x, in place of b, 2. So 24x square plus 11, this is equal to 2 is completely multiplied by, first we have 3x whole squared, then 2 times 3x times 2. So this is plus 12x and then plus 4 and then plus 3. So 24x square plus 11 is equals to 18x square plus 24x plus 2 times 4 is 8 and then plus 3, this will give you 11. So 11 and 11 are cancelled out over here. Okay, so what you are left with, 24x square minus 18x square minus 24x is equals to 0. So 24 minus 18 is 6. So 6x square minus 24x is equal to 0. So taking 6x is common, multiplied by x minus 4, and this whole thing is equal to 0. So 6x is equal to 0. So this means x is equal to 0 and x minus 4 is equal to 0, meaning x is equal to 4. But here we also need to see what is the domain of the inner function. Since we are dealing with f of gx and we are dealing with g of f2x as well. And as we know the matter of fact that both of the functions fx and gx, they have their own domains which are x is greater than or equal to 0. Both have the same domain. Both of the functions fx and gx, they have the same domain, x is greater than or equal to 0. Okay, so we need to see the domain of the inner function. Okay, and we need to also see the domain of the function g of f2x, which will be exactly the same as the domain of the inner function f of x. Okay, so in conclusion, both of the functions fx and gx have the restriction x is greater than or equal to 0. So we just need to see if our answers are according to this domain of the inner function. So yes, both of the answers are according to this domain. So x is equal to 0 and x is equal to 4. Both are acceptable over here. Both are your answers. All right. You need to see each and every time. You need to consider the domain of the inner function whenever you are solving the equations which are related with the composite functions. Okay. Yes, if the inner functions do not have any restrictions, okay, if the inner functions do not have any restriction, like x can take any real values, so in that case, it's completely fine. All of the answers would be accepted. But when there is a restriction on the inner function, the domain of the inner function, you need to consider your answers accordingly. So in this case, both of the answers, x is equal to 0 and x is equal to 4 are acceptable. All right. So this was the question, which is handout question number 27, February, March 2017, paper 1, variant 2, question number 8. All right, so now let's see another question, which is handout question number 28. Okay, this question is not specifically on the domain and range of composite functions, but still it is on the topic of functions, so it deals with inverse functions as well. So this is question number 28, May, June 2017, paper 1, variant 1, question number 9. All right, so the question says that the function f is defined by fx equals 2 divided by 3 minus 2x for x can take any real values where x is not equal to 3 over 2. Okay, because at x is equals to 3 over 2, this function fx will have a vertical asymptote, meaning the function is not defined for x is equals to 3 over 2. Okay, so this means that x is not equal to 3 over 2. Find an expression for f inverse x. So simply we need to perform the steps of finding the inverse function. So y is equated with fx. So y will be equals to 2 divided by 3 minus 2x. Okay, so now in the next step, I'm going to expand this. Okay, so 3y minus 2xy is equals to 2. And now I'm going to keep x on one side and the terms related with other than x on one side. So 3y minus 2 is equals to 2xy. So x is equals to 3y minus 2 completely divided by 2y. And now in place of x, I'm going to write f inverse x, and in place of y, I'm going to write x. So f inverse x is equals to 3x minus 2 completely divided by 2x. So either you can write your answer in this form, this is expressed as a single fraction, or otherwise you can also say that since f inverse x will be equals to 3x over 2x minus 2 over 2x, so therefore f inverse x is equals to 3 over 2 minus 1 upon x. As simple as that. Both of the forms would be acceptable. All right. So this was the answer of part 1. So now in part 2, it says that the function g is defined by gx is equals to 4x plus a for x can take any real values where a is a constant. Find the value of a for which g of f minus 1, meaning gf minus 1 is equals to 3. Okay, so when you say that gf minus 1, this means that input of the gx function is f minus 1. So first of all, we should find f minus 1, and for that purpose we have fx function, which is 2 divided by 3 minus 2x. So input of fx function is minus 1, so output is 2 divided by 3 minus 2 times minus 1. Okay, so 2 divided by 3 plus 2, meaning 2 over 5. The value of f minus 1 is 2 over 5. So now this will become the input of the gx function. So we need to find g2 over 5, which is exactly the same thing as saying gf minus 1. So this g2 over 5 is equals to 3, as we know that gf minus 1 is equals to 3. So now we have this condition, g2 over 5 is equals to 3. So 4 times 2 over 5 plus a is equals to 3. All right. So 4 times 2 is 8. So 8 over 5 plus a is equals to 3. Therefore, a is equals to 3 minus 8 over 5. 3 minus 8 over 5. This is how much? This is supposed to be 7 over 5. All right. So the value of a is 7 over 5. This was the answer of part 2. Okay, so now we have part 3. Part 3 says that find the possible values of a given that f inverse x is equals to g inverse x has two equal roots. Okay, so f inverse x we have already found in part 1. So now we are going to find g inverse x first in terms of a. So I'm going to do some working for part 3 over here. So first of all, we need to find the g inverse x function. So y is equals to gx, meaning y is equals to 4x plus a. So 4x is equals to y minus a, meaning x is equals to y minus a completely divided by 4. So therefore, g inverse x is equals to x minus a completely over 4. Okay, this is the g inverse x function. So f inverse x is equals to g inverse x. This means that 3 over 2 minus 1 over x is equals to x minus a completely divided by 4. So I'm going to express this f inverse x as a single fraction, which I already obtained this expression as well. 3x minus 2 completely divided by 2x. This is equals to x minus a completely over 4. So I'm going to do cross multiplication over here. So 4 times 3x minus 2 is equals to 2x multiplied by x minus a, meaning 12x minus 8 is equals to 2x square minus 2ax. So now I'm going to collect all of the terms on one side. So 2x square minus 2ax minus 12x plus 8 is equals to 0, meaning 2x square plus taking x as common multiplied by minus 2a minus 12 plus 8, and this whole thing is equals to 0. So therefore, I have obtained a general form of the quadratic equation, which is ax square plus bx plus c is equals to 0. So therefore, I can say that a is 2, b is minus 2a minus 12, and c is equals to 8. So far, we have achieved this thing. And now the condition is that it has two equal roots. So when we have two equal roots, so b square minus 4ac is equal to 0. B square minus 4ac is equal to 0, meaning the discriminant of the quadratic equation is equal to 0. Under this condition, we need to find the possible values of a. Okay, so this means that minus 2a minus 12 whole squared minus 4 times 2 times 8 is equal to 0. Okay, so minus 2a minus 12 whole square is equals to 4 times 2 times 8. So this will be equals to 64, meaning, uh, I mean, if you don't expand this, if you take a square root on both sides in this step, so that's also fine. So taking square root, so minus 2a minus 12 is equals to plus minus 8, meaning plus minus under root of 64. So far we have achieved this thing. So now we can say that minus 2a minus 12 is equals to 8, or minus 2a minus 12 is equals to minus 8. So this means that minus 2a is equals to 8 plus 12, which is 20, and a will be equals to 20 divided by minus 2. Therefore, one value of a is equals to minus 10. Okay, one value of a is minus 10, and the other value of a would be minus 2a is equals to minus 8 plus 12, which is 4. So a will be equals to 4 divided by minus 2. Therefore, a is equals to minus 2. So these are basically the two possible values of a. One is minus 10 and the other one is minus 2. This is supposed to be our answer. All right. So this was the question number 28 of the handout, which is May-June 2017, paper 11, question number 9. All right. So now let's move on to question number 29 of the handout, which is May-June 2017, paper 1, variant 3, question number 9. Part 1 says that express this expanded form 9x square minus 6x plus 6 in the form ax plus b whole squared plus c, where a, b, and c are constants. Okay, so first thing first, we have an expanded form
ax square plus bx plus c. And in order to convert this expanded form into a completing square form, basically my approach is to use this formula, which is a times x plus b over 2a whole squared plus 4ac minus b squared divided by 4a. Okay, the formula for converting an expanded form of the quadratic expression into a completing square form. So here we can see that if we make a comparison with the form of this expanded form which is given to us in the question, we can say that a is equals to 9, b is equals to minus 6, and c is equals to 6. So what I'm going to do, I'm going to plug in these values into this formula. Okay, the formula for completing square. So I can say that in place of a, I'm going to write 9 times x plus minus 6 over 2 times 9. This is whole squared, and then plus 4 times ac minus b square divided by 4a. Okay, I've used the values of a, b, and c over here. So therefore, I'm going to say that first we have 9 multiplied by x minus 6 over 18. So 6 over 18 is 1 over 3. So x minus 1 over 3 whole squared, and then plus 4 into 9 into 6. Subtract 36 divided by 36. This is positive 5. Okay. But we need a specific form over here in which the coefficient of x inside the bracket is a. And the form which I have obtained over here, the coefficient of x inside the bracket is 1. Okay, so I'm going to perform some additional steps over here in order to convert this into the required form of this particular question. Okay, so for that purpose, what I'm going to say that this can be, expressed as 3 squared times x minus 1 over 3 whole squared and then plus 5. Okay, and according to the rules of indices, the laws of indices, we can say that if you have a squared times b squared, it is exactly the same thing as saying a times b whole squared. All right, this makes sense. So I can say that 3 times x minus 1 whole squared and then plus 5. What I've done is that I have multiplied this 3 with this bracket x minus 1 over 3. So when this is multiplied, it comes into the required form. So 3x minus 1 whole squared plus 5. All right. In this way, I have converted the expanded form into the completing square form, which was required in the question. Okay, and now I can say that if I make a comparison with this form, ax plus b whole squared plus c. So therefore, a is equals to 3, b is equals to minus 1, and c is equals to 5. You don't need to mention these a, b, and c in the final step. Your final step was this required form, which you obtained over here. 3x minus 1 whole squared plus 5. As simple as that. Usually what happens is that the completing square form is required in this particular manner: a times x minus h whole square plus k. Okay, where the coefficient of x inside the bracket is 1. All right. So what we do is we use this particular formula and then we obtain the completing square form. However, in this particular question, the required form was something else. It was ax plus b whole squared and then plus c, meaning the coefficient of x inside the bracket was a. And according to the requirement of the question, we have obtained this form. Here we have an alternative approach as well. Alternative approach is to use the equating the coefficients method. Okay, so I'm going to solve this by an alternative method as well. What we need is a form which is ax plus b whole squared plus c. Okay, and this is basically identical to the expanded form of the quadratic expression, which is 9x squared minus 6x plus 6. So here I'm going to use this alternative approach, that is equating the coefficients method. So what I'm going to do, I'm going to find an expanded form in terms of a, b, and c. So I'm going to say that ax whole squared plus 2 times ax times b plus b squared and then plus c. Okay, so I'm going to say that a square x square plus 2abx plus b square plus c. This is equivalent to this expanded form which is given to us in the question, 9x square minus 6x plus 6. So first of all, I'm going to equate the coefficients. As I can see that the coefficient of x square is a square, and here the coefficient of x square is 9. So therefore, I'm going to say that equating the coefficients of x square with each other, a square x square is identical to 9x square. So therefore, I'm going to say that a square is equals to 9, and therefore a is equals to plus minus 3. Okay, and as you know the fact that, in the expanded form, the coefficient of x square is positive. In the expanded form, the coefficient of x square is positive, so I'm going to take a is equals to 3 over here. Okay, in order to be consistent with our question. All right, so since the coefficient of x square is positive, okay, so I'm going to take a positive value of a over here, which is 3. And now in the same way, I'm going to equate the coefficients of x. So I'm going to say that 2abx is exactly equivalent to minus 6x. Therefore, equating the coefficients of x with each other, 2ab is equals to minus 6. Therefore, a is 3, so 2 times 3 times b is equals to minus 6, so b is equals to minus 6 over 6. Therefore, b is equals to minus 1. Okay, and then the constant term, so b square plus c will be equivalent to 6. Okay, the constant term is independent of any variable. The constant term is independent of x and x square. So therefore, I'm going to say that b square plus c is equals to 6. And we have obtained the value of b. So this means that minus 1 whole squared plus c, this whole thing is equals to 6. So this means that c is equals to 6 minus 1, meaning c is equals to 5. Okay, so we have obtained a, b, and c according to our requirement. And now we are going to say that the required form is 3x minus 1 whole squared plus 5. Okay, so in both of these ways, you can attempt your part 1. All right, so now let's move on to part 2. It says that the function f is defined by fx is equals to 9x square minus 6x plus 6 for the domain x is greater than or equals to p, where p is a constant. The requirement of part 2 is state the smallest value of p for which f is a one-to-one function. Okay, so now um, what we know the fact is that in these type of questions, the domain is restricted from the x coordinate of the turning point of the quadratic graph. Okay, so in this case, we obtained the completing square form, which was 3x minus 1 whole squared. Okay, which was 3x minus 1 whole squared plus 5. So here we have the equation of the curve. So I can say that this is the fx function. Okay, fx equals 3x minus 1 whole squared plus 5. So this 3x minus 1 will be equated with 0. Okay, so therefore I can say that x is equals to 1 over 3 and y is equals to 5. So therefore I'm going to say that 1 over 3 comma 5 is the turning point of the quadratic graph. So if there was no restriction on the domain, so the graph would look something like this, that the turning point was at 1 over 3 comma 5, meaning the turning point of the graph is at completely above the x-axis. Okay, so the graph would look something like this if there was no restriction on the domain. Okay, x is 1 over 3 and y is 5. This is our turning point. However, what we need to find the smallest value of p for which f is a one-to-one function. So as you know the fact that only one-to-one functions have inverse. Those functions which are not one-to-one, meaning those functions which are any to one, they do not have inverse. So from the x coordinate of the turning point, I'm going to restrict this quadratic graph. So I'm going to erase all the other parts now, and I'll keep it for the domain x is greater than or equals to p. So therefore, I'm going to say that x is greater than or equals to 1 over 3. This is the smallest value of p for which one-to-one function exists. Okay, let's say if I take a value x is equals to 2 over here. Okay, if I take a value x is equals to 2 over here, and if I say that x is greater than or equals to 2, so yes, I would say that it is a one-to-one function, but this would not be the smallest value of p. We need to tell the smallest value of p for which f is a one-to-one function. All right. So smallest value of p is 1 over 3, meaning the x coordinate of the turning point of the quadratic graph. Okay, so for just 1 mark, you need to state this thing that x is greater than or equals to 1 over 3. Therefore, the smallest value of p is 1 over 3. The smallest value of p is 1 over 3. All right. So in this way, we have attempted this part 2. All right. So now let's move on to part 3. Part 3 says that for this value of p, obtain an expression for f inverse x and state the domain of f inverse. Okay, so I'm going to do working for part 3 over here. Here I have some space on the same page. So I'm going to find f inverse x. So the steps to find the inverse function, first of all, we keep the fx function equals to y. So y is equals to fx, meaning y is equals to 3x minus 1 whole squared plus 5. Okay, so y is equals to 3x minus 1 whole squared plus 5. And then I'm going to say that 3x minus 1 whole squared is equals to y minus 5, meaning when we take a square root on both sides, so 3x minus 1 will be equals to plus minus under root of y minus 5. So 3x is equals to 1 plus minus under root of y minus 5. So therefore, we are going to say that x is equals to 1 over 3 plus minus 1 over 3 times under root of y minus 5. All right. So now when we are going to write f inverse x in place of x, and in place of y, we are going to write x. So we have to choose which sign to keep over here, either the plus sign or the minus sign. Okay. And for that purpose, first I'm going to leave some space over here for the sign which I need to keep. And now I'm going to see what is the range of f inverse x. Okay. I need to find the range of f inverse x. And for that purpose, I'm going to find the domain of fx. So the domain of fx, we have already seen that x is greater than or equals to 1 over 3, which is basically the domain for which f is a one-to-one function. All right. And we have seen that the domain of fx is that domain of fx is that x is greater than or equals to 1 over 3. So this will become the range of the inverse function, range of f inverse x. So f inverse x will be greater than or equals to 1 over 3. So we need the outputs of f inverse x to be greater than or equals to 1 over 3, and that would be only possible if we add something into 1 over 3. So therefore, I'm going to say that f inverse x is equals to 1 over 3 plus 1 over 3 times under root of x minus 5. This is basically the f inverse x function. And now we also need to tell the domain of F inverse. Okay. And for that purpose, we need to see what is the range of fx. And as I've already sketched the graph of fx, so by observing the graph, I can say that the range of fx is that fx is greater than or equals to 5, meaning fx is greater than or equals to the y coordinate of the turning point of the quadratic graph. This is basically the range of fx. And now the range of fx will become the domain of f inverse x. So therefore, I'm going to say that the domain of f inverse x is that x is greater than or equals to 5. This was also the requirement of part 3. Okay, the range of fx becomes the domain of f inverse x. And in order to find the range of any function, always helpful to sketch the graph, which I have already sketched above. All right, so now we have part 4, which says that state the set of values of q for which the equation fx is equals to q has no solution. And this part 4 is worth 1 mark. So we can use the graph of fx over here as well. So fx equals to q means, you know, if anyone says to you that you have an equation fx is equals to q, this essentially means that you are observing the point of intersection between the graph of fx and the line which has the equation y is equals to q. The horizontal line y is equals to q. So I need to make the horizontal line y is equals to q in such a way that there are no intersection between the graph of fx and the line y is equals to q, meaning the equation fx is equals to q has no solutions. Okay, so I'm going to make the horizontal line in this way, which is below the turning point of the quadratic graph. Okay, because I don't need any solutions over here. Okay, under this condition, I need to tell the set of values of q. So q is below the y coordinate of the turning point. If q was equals to 5, then you would have said that yes, it has solution. It has a solution. If q was greater than or equals to 5, you would also have said that, it has a solution. Fx is equals to q has one solution over here. Okay. But in this case, in the required form, fx is equals to q has no solutions. So therefore, q will be below 5. Therefore, our answer to part 4 will be simply q is less than 5. Okay. If the requirement was that fx is equals to q has a solution, so you would have said that q is greater than or equals to 5. Because if you keep q is equals to 5 or any value above 5, you would have one point of intersection with the line y is equals to q and the graph of fx. But in this case, we don't need any solution of the equation fx is equals to k. Therefore, our answer will be q is below 5. Q is less than 5. Okay, so it was worth 1 mark only. So you just need to state this thing. So these were some questions from past papers of A-level mathematics, Cambridge, P1 functions topic. Inshallah, I'll be uploading more videos, more content on A-level mathematics. So stay tuned to my channel. Thanks for watching. Assalamu alaikum.